first of all, thanks to the organizer for the possibility to present this work. So I'm going to present the combined dark matter search with Fermi-LAT, HAWC, H.E.S.S, MAGIC, and VERITAS. So this collaborative effort gathers 16 people whose names appear at the bottom here. And I'm going to talk on behalf of these 5 collaborations. So as you know, dark matter represents about 85% of the total matter of the universe, and its identification would reveal new physics. And proving its existence and nature would improve our understanding of the universe. And with these 5 experiments, these 5 collaborations, we decided to combine all the observations results that we have towards the dwarf spheroidal galaxies. Oops. In order to improve significantly the statistics that we have, and also the sensitivity to potential dark matter signal. And we're going to use all individual results already published by individual collaborations. Okay, I have trouble to skip to the next slide. Okay, so as you know, in dark matter search framework, so we have dark matter particles that will annihilate to give standard model particles such as boson, quarks, and leptons, and which then give final state products such as gamma rays. And the expected gamma ray flux from a given source is then given by this equation, where you have a particle physics factor here with the sigma v annihilation cross section. And we have a second element, which is the astrophysical J factor. So we focused on the dwarf spheroidal galaxies, which are systems with few bright stars. And we distinguished 2 different kinds. The first one is the classical one that contains about 2,500 bright stars. And in ultra-faint, you can find only up to a few tenths of bright stars. So it's not too much tracers to reconstruct the dark matter profile. These systems also have low to no gas, dust, or recent star formation. And they are also dark matter dominated objects. And the advantage is that they do not have any expected astrophysical gamma ray background, and which make them ideal laboratories for dark matter indirect searches. So here are the 20 targets that we're going to use in this combined analysis. So we have 20 classical or ultra-faint dwarf galaxies, and they were all observed by either one or several experiments that you can see here. And as I said before, they were all published separately in the past by individual collaboration. So here are the 5 experiments that will combine the results. So at the beginning of the spectrum, we have Fermi-LAT. And at the end of the spectrum, we have the 3 air imaging Cherenkov telescopes with MAGIC, H.E.S.S, and VERITAS. And we also find the HAWC experiments, the warrior Cherenkov detector. And with these 5 experiments, we can cover the widest energy range ever investigated. And to perform a combined analysis, we need common ingredients. So after many exchanges between all collaborations, we find an agreement to homogenize the statistical approach and derive the observed, the mean expected limits, and also the uncertainty bands. And we had to agree on the data sharing. So we use a common format of test statistics value versus the annihilation cross-section sigma v. And we will perform the analysis using 8 different annihilation channels. So here in this presentation, I will show you the tau channel and the BB bar channel. We use the spectrum of Chiarelli, and the J factor is taken from Gerger-Samet publication. And in this profile, this J factor derivation, they use a dark matter profile, Zhao-Hernquist, which is a generalized dark matter density distribution. And you can see here 2 examples of J factor distribution. So we have Carina a classical dwarf that has few uncertainties on the J factor compared to the sigma way, which are greater than a classical one. And here is the formula for the log likelihood ratio test statistics to perform the combined analysis. So here is the test statistic value, which corresponds to fraction between two likelihood functions. The first one will be minimized globally on the parameter of interest and also the nuisance parameter. And the numerator will be minimized with a constraint. That this means that we're going to fix this value sigma v, and we're going to minimize the function on the nuisance parameter only. And once we reach 2.71 for the test statistic value, this means we will reach the 95% confidence level for 1 degree of freedom. So here is the shape of the likelihood function. So we have one likelihood function per experiment and per object, per dwarf galaxy. And we're going to have a nuisance parameter for the J factor to introduce the nuisance parameter on this J value for each of the dwarf galaxy. And all of these likelihood function will then be multiplied for all of the objects that we have and for all experiments. And we perform the combination using two independent public analysis software. The first one is JLike, and the second one is likelihood combiner. And graphically, this is what the combination looks like. So we have here the global minimum. This is the denominator of the test statistic function. And this is the constraint value, so the numerator value of the fraction. And we found the upper limit on sigma v at 95% for a given channel, a given dark matter mass, and dwarf and experiment as well. And this is so for only one dwarf, only one experiment. And if we want to combine these limits, so we need a test statistic profile for each of the experiments. So here is an example with 4 experiments. And we're going to do the sum of all these profiles to end up with the black line here. And you can see that all the minimum, so the first one, the global minimum, will be shifted to the smaller value of sigma v. And same for the constraint minimum here, it will be shifted to the smaller value. And we can get back, retrieve the new upper limits at 95% confidence level on sigma v here. So this is how we improve the upper limits using a combination on the results with multiple experiments. So since we have no significant excess found in the data, so we derive the upper limits using this statistical analysis. And we perform the derivation of observed limits from the collected data, and also the expected limits from a sample of 300 Poisson realization on the background event produced by each individual experiment. And from these expected limits, we found the mean expected limits from which corresponds to the derived sigma v distribution. And we also have the statistical uncertainty bands that we derive from the standard deviation at 1 and 2 sigma. So this is 2 examples for the BB bar channel and the tau channel. And you see here in colors that we have the upper limits derived by individual experiments. So we have the 5 individual experiments here and here. And the black line corresponds to the observed limit using the combination. And the dashed line corresponds to the mean expected limit with the uncertainty bands at 1 and 2 sigma in green and yellow. And overall, we have an improvement of 2 to 3 times more constraining of these new upper limits using all experiments. And we can see that the first part of these limits corresponds to to the sensitivity of the different experiments. So we have Fermi-LAT for the first part, and then we see that the ISTT's experiment and HAWC contributes significantly on the second part. And we have to note that these upper limit profile depend on the choice of the annihilation channel. And they are also driven by the object with the highest J factor that can be observed by different experiments. And we also have to note that the ultra-faint dwarfs, such as sigma 1, can be subject to large systematic uncertainties for the determination of the J factor. So we finished this presentation with this conclusion. So we have no significant dark matter signal observed by any of the experiments, nor in the combination. So we used likelihood profiling and common ingredients to derive the upper limits on the annihilation cross-section. And we do that over the widest mass range ever for the dark matter WIMP particle. And we combine the upper limits, which gives an improvement of 2 to 3 times compared to the individual limits obtained by the different 5 experiments. And in the future publication that is still in progress, we will have 6 additional channels. And we will also perform the analysis with the second set of J factor to study the impact on our upper limits using this second determination of J factor. And that's it for me. So thank you for your attention.